Well, it's my great pleasure to welcome James Lewis. We're very thrilled that he accepted our invitation. And for those probably few, if that's even the case, who don't know James, he's a software architect and the director at ThoughtWorks. He's also one of the people whom we have to thank for the concept of microservices that we have today. So I think that's quite important.
One thing I love from James's talk is that he points out that research from Santa Fe Institute seems to point to a grand unified theory of organizational design. So that makes me wonder, are we close to saying like this is the way to build software? You know, like lucky people doing construction work have been doing for I'm gonna say centuries, but most likely I'll be wrong. You know, at least centuries. Are we getting? I'm really curious to know if we're getting any closer to the one true way of developing software, of organizing software.
I think we have the right person to ask. So hi, James.
Yeah.
Welcome at Codecamp.
I guess you're just running through the intros, yeah?
No, we're done. So welcome at Codecamp. We're thrilled to have you here.
Thank you for inviting me. It's a real pleasure. So I don't know if you know, we actually opened, well, rather, we now have a ThoughtWorks Romania.
Yes, I heard. So it's
quite exciting.
Yeah, maybe it will be opportunity to travel in person whenever that will be possible. But it would be great to have you here.
When it's possible, I'd love to come. I visited for, I think it's the ITake conference some years ago. I had a great time at that. So I think it was me and Simon Brown traveled. But yeah, I mean, I'd love to come at some point. But thanks for the invite. So it's a real pleasure to be here.
Plus, there are also some advantages to being online because the audience is broader. If I look at how yesterday went, I think we had around 1,700 people throughout the day, and they are a lot of them are from Romania, but also we have audience from all over the world. I think we're missing Antarctica. So if anybody in the audience knows somebody there, send them the link so they can check that box.
Yeah, if I had a direct into the people at the British Antarctic Survey, maybe we could get some of the geophysics people down there to get on the call, but I'm not sure about that.
Let's keep it in mind for next time. But then coming back to Vlad's question or remark, how do we stand in terms of software architecture? Are we getting closer to, I don't know, being more of a recipe like in construction?
It's interesting, isn't it? I mean, if you ask Dave Farley about that, he'd sort of say, I think Dave is a friend of the conference, isn't he? I think Dave would say, channeling Dave, in fact, he'd sort of talk about how we are moving closer to the sort of repeatable processes that are found in other engineering disciplines, you know? So the fact that we've got continuous delivery, the fact that we can, you know, have bake quality in through automated testing early on in our build pipelines, the fact that we have such a focus on quality and observability and all these different things. I think that does bring us closer towards a repeatable process. I think what the interesting thing about this, the research that Santa Fe sort of talks to is, you know, we struggle all the time with organizational reorganizations, and then, you know, how do we run teams? Is it products or projects? And it sort of points to this idea that actually, in order to maximize your return, whether that's through, you know, in terms of monetary return or in terms of information flow, then you should be looking to organize in a particular way. And that's true, you know, for the organization, but also therefore for the software architecture. And I think that's the interesting thing, is the intersection between Conway's law and the organizational design side of things and the software architecture side of things, you know. So yeah, I think we're on our way. I don't think it's done, right? I mean, there's a whole bunch of interesting things to explore. I think actually, if you look at the Team Topologies book, I'm pretty sure you're probably aware of Team Topologies. which came out, Skelton et al. I can't remember the other writer, the other author, but that sort of describes a set of common team shapes, you know, that seem to be advantageous, shall we say. And I think that's part of this as well, you know, the sort of how your team is shaped, how the organization is shaped around social networks, and how your software architecture is shaped around loosely coupled cohesive capabilities. So yeah, I think we're getting there, but I mean, you know, this is just me shouting into the void at the moment, you know, old man shouting at clouds, right? So.
Yeah, but indeed, while I was reading your abstract, I was looking forward to the talk, because these two are indeed linked. The way your company is organized, and especially your teams working on a project, that is reflected in the architecture as well. All right, so let's say without further ado, we can give you the floor, and then we can regroup in 40-45 minutes to talk some more about this.
Okay. What are we doing? So I need to share my screen. That's going to be a good start, isn't it?
Yeah, I think we can see it. Just before you start, I just want to tell everybody out there to feel free to ask questions in the chat, and Vlad and I will pick them up at the end of James's session, and then we can tackle them. Yeah. That's it from me.
Okay, so right, so where do we start? So I like this slide. This is this idea that actually, if you looked at Earth from orbit, what you would see at night is this tremendous network of lights lighting up across the entire planet. And I like this idea, this quote from the Santa Fe Institute, the Interplanetary Festival they held, that if an alien visited Earth, they might well think that cities were the dominant form of life, and that the humans that live in them were their microbiome, the equivalent of gut bacteria in humans. Which I think talks to something quite profound, in the sense of we're building these bigger and bigger edifices, both in terms of things like cities, but also the organizations in which we work. And you know, what are the consequences of building these bigger and bigger things? What are the properties of these bigger and bigger things? So let's get on to this, I guess, in a bit more depth. So this talk today is called Scale, Flow, and Microservices. And it's about the intersection of a number of interesting things. So the intersection of things like lean product development, so the concept of flow, but also the concept of flow in terms of fluid flow through different structures, things like pipes, and and actually information flow through organizational hierarchies. It's about scale, but in terms of scaling software, yes, and scaling teams, but also in terms of how power laws point to different scaling laws within the natural world, both in terms of companies and in terms of cities and in terms of mammals. And it's all based on some work, some original research out of a number of people at the Santa Fe Institute, which I'll link to at the end. And it's also about microservices. So let's maybe come to that first. So Martin and I originally said that we cannot say there's a formal definition of the microservices architectural style. This is when I went for a sleepover back in 2014. That seems like a long time ago now. What we did say is that there are these characteristics, these properties that we've identified that seem to be shared across architectures that you can describe as a microservice architecture. So these are things like componentization by services, or business capabilities, or decentralized data management, pushing the smarts out into the endpoints, not having them in say, NESB in the center, decentralization of governance and so on, and products, not projects. And over the years since we sort of published that paper, I've sort of been thinking about whether there are other categories of things, whether there are underlying principles behind microservices and architectures and service-oriented architectures, and therefore the organizations that adopt them. And because a lot of these things are, as I say, talking to decentralization, to pushing things to the edges, to moving away from hierarchies, to building cohesive, decoupled, independent things that talk to each other via smart endpoints, APIs. And then, of course, componentization via services of breaking things up into smaller bits. How small? Well, that's up for debate, obviously, but just not about that big, I guess, is the answer. haha. It's hard to get jokes in when you're talking, shouting into the void. So I guess the question is, are there some underlying principles behind the ideas in sort of embodied in that idea of microservice architectures? So there's sort of the idea of, you know, is there an underlying physics, and almost like an algebra almost, of microservices, and what might that look like? And I've come to the conclusion that I think there is a set of underlying principles, but they're quite surprising, and I sort of found them in a surprising place. So the start of this story, my journey, is in Anguilla a couple of years ago. This is Shoal Bay East. It's commonly on the list of top 10 beaches in the world. And I was there for a workshop where we were exploring a number of topics, including Conway's Law, actually because Mel Conway was actually at the event. So we spent some time talking about things like how we'd applied Conway's Law to our software architectures, to the organizations in which we worked. And as part of that discussion, someone who shall remain nameless but works at Amazon started talking about how at Amazon, the faster they get bigger, the easier it is to get bigger. So the bigger we get, they said, the easier it is to get bigger. The more people we add, the more people we can add. The more products we build, the more products we can build. And that sort of, you know, on reflection, really sort of stunned me. I was sort of thinking that night, well, that flies in the face, really, of received wisdom, which is, you know, going back to the Mythical Man Month, you know, this idea that adding manpower to a late software project makes it later. You know, and if the fundamental reason, talked about in that seminal work, is around communication overhead, information flow, the need to coordinate as you add more people. Now, one of the things originally with microservices was, you know, we wanted, you know, the idea of breaking things up into, or decomposing things such that we could bring more people to the party, if you like. If you've got independent bits of your software architecture, then more, you know, you can have independent teams working independently on them, which is, you know, it does to some extent fly in the face of this. But the idea that an organization of Amazon's scale can get faster the bigger it gets, that seemed to be to me unusual. I would take a show of hands to say, you know, who works in a company where that happens, because I think there'd be very, very few hands actually raised. So then I went home, and being a bit of a nerd, I sort of tried to dig out some figures as to whether this might be true. And this is, I admit, data scientists out there, you know, this is limited number of data points, but this is actually an old graph now. What this shows on one axis is revenue growth. It's log, is revenue growth. And this is, sorry, it's not log. I shouldn't say things that are wrong. It's log on one axis and it's not log on the other axis. And what this shows is revenue growth versus employee count at Amazon over the last number of years. And what we can see is a sort of generally a straight line, and we can see this exponent which says 1.15. Now, any exponent here above 1 means that as they're growing, they're making more money than they should. So if you think as you double in size, you might double the amount of revenue you're bringing in. Ideally, actually, as Amazon are doubling in size, or AWS in particular, they're actually bringing more than double the amount of revenue into the organization. And again, that made me pause and think maybe there's something going on here with both, you know, with AWS, but also with the wider way that AWS and things are organized. So it brings me to what is almost certainly a brief and incomplete introduction to something called nonlinear dynamics and complexity science, or complex adaptive systems. So here's a question which I'll have to ask rhetorically, of course, at this point. But what do mice and elephants have in common? And this, or any mammals actually, in terms of mammals of different sizes. And the interesting thing is that as you double the size of an animal, of a mammal, so as you go from, you know, something like a rat up to a pigeon, say, what you would expect to happen is that you would expect them to have eat double the number of calories, because they've got, you know, they're twice the size, so they need double the amount of energy. But actually that doesn't happen at all. Actually what happens is, as you double the size of a mammal, they only need about 75% of the calories they should. And this is down to a number of factors which we'll come on to in a minute. There are some things that stay the same though between different mammals. So it was a surprise to me when I found out that all mammals share approximately the same number of heartbeats in their lifetime. It's just the heart rate which changes, essentially. So, you know, a very short-lived animal, like a bird, or, you know, a shrew, say, will have the same number of heartbeats, as an elephant or a whale. They'll also have the same blood pressure, which again is quite peculiar. And as I say, as they double in size, they only need 75% of the calories. Their metabolic rate, in other words, it scales with a scaling law of 3/4, 0.75. So as a mammal doubles in size, it only needs 75% of the calories. So what is another sort of different domain, but what do, say, mom and pop stores and, say, large giant supermarkets have in common? Well, actually, if you look at revenue versus employees, as I did in that graph with Amazon earlier, or AWS earlier, in general, the slope is also about 3/4. In fact, with some errors, it comes out to about 85%. So as you double the size of a company, the number of people in it, you don't double the revenue that you get out. You actually get about 85% out, 85% of the revenue. So again, it follows the scaling law with a particular exponent, 0.85. Here's another example. What do Hamburg and Leipzig, say, have in common, or other cities that are approximately doubling in size to one another? Well, for these cities, infrastructure scales with an exponent of 0.85 as well. So as you double the size of a city, you only have to spend 85% on public infrastructure. So things like sewage pipes, things like telephone cables, things like telephone poles, and so on. So infrastructure scales with a population with an exponent of 0.85. So that's, as I say, road length, petrol stations, electricity cables, number of restaurants, and so on. You get 85% of the number that you would expect as you double. So all these three things, these straight lines in different domains, in terms of how organizations scale, in terms of how biological life scales, and in terms of how cities and villages and things scale. There's all these straight lines here, and they've all got these exponents with a value that's less than 1. And what we call that is economies of scale. As you double in size, you get an economy of scale for infrastructure in cities, for example, and in organizations. And you also get economies of scale for metabolism, for calorific intake in mammals. So Geoffrey West, the author of the book Scale, linked to at the end of this, he sort of has this, he makes this statement that quantities that do not change when other parameters change, they play a special role in science. And I originally I read physics as an undergraduate, and this was sort of drilled into you. When you start to see these interesting patterns, you should look for things. You should look for underlying principles. Look for the underlying reality. So as I say, these are examples of scaling laws. And so on a log-log graph, if you double one quantity and you get double the other quantity out, that means you've got linear scaling. It's plotted as a straight line here, but if you plotted it not on a log-log graph, it would look like an exponential curve. This is otherwise known as exponential growth. If you double one number and the other number increases by less than the same amount, that's known as sublinear scaling or economies of scale. So this is the sort of thing, as I say, we get with cities with infrastructure and companies with infrastructure and so on. So all this stuff leads back to an organization, a sort of a research institute in Santa Fe in the US in New Mexico, known as the Santa Fe Institute. It was created a number of years ago now to study complexity science by a group including some Nobel Prize winners, one of which was Murray Gell-Mann, who worked a lot with Richard Feynman. Murray Gell-Mann was fascinated by the idea of how you could get such complexity, such complex things such as like life from the simplest possible components like quarks and atoms. And he wrote a book actually about this called The Quark and the Jaguar. And he was instrumental in setting up this institute to study this idea of complexity science or complex adaptive systems. So what is a complex adaptive system? Well, a complex adaptive system can be explained by 3 simple properties. A complex adaptive system is a system where you get emergent complexity from simplicity, essentially unplanned complexity from simplicity. And all of those scaling laws which relate to complex adaptive systems, a city is a complex adaptive system, so is a company, so is a human, so is the teams we work on, so is the software that we're building, so is the architectures that we're working within, or both in a runtime sense. These scaling laws can all be explained by 3 very simple principles. So the first one of these principles is the idea of space-filling fractal networks. So this is here an example of a hierarchy, a hierarchical space-filling fractal network. So you can think of these in terms of your blood supply. Your circulatory system is a space-filling hierarchical fractal network. The roads in a city are a space-filling hierarchical fractal network, as are the water supply, essentially, to a city. And in companies, you have, for example, network cables. They form hierarchical space-filling fractal networks, as do the flow of information through the company, through our teams. The next thing the next of the principles that goes to explain these scaling laws is the idea of an invariant terminating unit. So in the network, things can be of different sizes, different shapes, but at the very end, the leaf nodes of the graph, if you like, they are the same size, the same thing. This is what I'm trying to persuade our HR department to start calling us, people in ThoughtWorks. Normally they call us meat bags as consultants, which is not very nice. So I thought, invariant terminating units might be slightly better than that, but still. So in companies, an invariant terminating unit is the person doing the work, right? So where the information ends up, where the work is generated. In a city, the invariant terminating unit is a residence, so it's where people live generally, and the people in it. And in biology, in mammals, in humans, the invariant terminating unit is the cells in our bodies. So they're all the same size. Our cells are the same size as a mouse's cells, are the same size as an elephant cells, give or take. Other things change within the system to explain the scaling laws, which I'll come to in a second. And the third necessary principle is this idea of optimization over time. So feedback loops. And we get different types of feedback loop in the different domains, right? So with biology, the feedback loop is evolution, and that acts on evolutionary time, geological time. There's a very long feedback loop. But in companies, there are much shorter feedback loops. In companies, it's about market forces acting, and so in cities, it is too. Market forces acting to cause feedback, to optimize the networks and to optimize the invariant terminating units. And with these three principles, we can explain those scaling laws. And when I mean explain, mathematically, they can be explained simply by these three properties of networks. An interesting thing, which I've sort of touched on, is that complexity and complex adaptive systems are absolutely everywhere. More or less everything you look at is a part of, or is itself, a complex adaptive system. So as I say, they can be described using three principles. And the key thing to take away from this is hierarchies imply scaling with an exponent of less than 1. So when you have hierarchies, you scale, you get less out as you double something than you might think. You get less. So as I say, with metabolism, you don't need as many calories. With cities, you don't need as many telephone poles, which is a good thing. You spend less money on that essentially. And I, for one, don't want to have to spend more money on food. I already spend quite enough. Thank you very much. So key thing, if you double something in size, you don't double the other thing with hierarchies. And as I say, they're everywhere. The teams we work in, the software systems that we're building, the organizational systems that we work within, they're all complex adaptive systems, and all display these scaling laws. Let's come on to an interesting thing now about companies and the experience of working in large companies or smaller companies as they scale to larger companies. So the question is, why do metabolic rates slow as size increases? As you increase the size of an animal, why does the metabolic rate slow down? And fundamentally, what it comes down to mathematically is it's a property of the hierarchy of the circulatory system, essentially. Because all of our cells are the same size. All the cells, they operate in a similar way. But with bigger animals, they operate more slowly. And that's down to the fact that we've got deeper hierarchies of blood supply. So if you look at a mouse, for example, or this is the Etruscan shrew, which is the smallest mammal it's mathematically possible to get. It's got the shortest number, it's got the smallest number of arteries between heart and capillaries and the cells, therefore. And that's essentially operating about as fast. It's just running around about as fast as it possibly can, lives for about 1.5 years. And then you've got a blue whale, which lives a lot longer, but operates in a lot slower fashion. It's got a gigantic heart, and it's got a very, very deep hierarchy of of arteries between its heart and the same cells that the Etruscan shrew has. And that the research shows that in that depth of hierarchy, the number of splits of arteries before it reaches essentially your capillaries, essentially where blood flow turns from a pumped, which is pumped, where you have a pulse in the artery, into the capillaries, which is a continuous flow to allow essentially nutrients across the boundary, energy across the boundary to the cells. The depth of that hierarchy, that explains the difference in metabolic rate. Because at the end, you've got these things which are the same size. But the hearts, clearly, are very, very different. This is an interesting fact. So bigger animals are more efficient, essentially, by about 75% as they double in size. And this is due to impedance matching in the circulatory system. It's essentially due to the fact that bigger animals over geological time, they've got this deeper hierarchies, but as the arteries split, they split into exactly the right amount to allow such that the blood flow is impedance matched across the boundaries. And this has happened because of evolution. The weird thing is, of course, if you didn't have impedance matching across an arterial split, what would happen is you'd get back pressure. You'd get essentially the heart trying to pump against itself. And this is essentially why things like plaque in our arteries build up. High cholesterol and plaque buildup is so bad because we're changing the size of our arteries, which means that we get back pressure up through the circulatory system, puts extra pressure on our heart. Our heart is doing extra work. And this has all happened because of evolution. It's all been driven by evolution. And this is an interesting thing. The same principles apply to companies and to hierarchies in companies. Bigger companies in terms of infrastructure are more efficient. As you double the size of an office building or double the size of a company, you only have to spend 85% of the money you think you should. You don't have to spend 100%. And again, this is due to these economies of scale relating to depth of infrastructure hierarchies. And companies are optimized by feedback from market forces as they grow. But the thing about companies as they grow, in the same way that animals slow down as they get bigger, essentially the cells of an elephant operate at a much slower rate than the cells of a mouse. The cells of a mouse are operating super fast and also having to be repaired super often, whereas an elephant cells aren't operating anywhere near as fast and therefore don't need as much repair. They don't suffer as much cell damage. Elephants don't get much cancer, for example, but they do operate they are slower. They are operating with a slower metabolic rate. The same thing happens with companies. Organizations, as they grow, they slow down for the same reasons. So if we look at the flow of work in organizations, we can maybe see why this, some of the effects of this or why this might happen in deeper hierarchies. So if you think about a hierarchy in an organization, the way information is flowing in an organization, when you've got information flowing through deep hierarchies, we get these very, very long, essentially process chains or value stream maps. This is one from an actual, from a client, an anonymized client I work with. And each of these little steps, takes some number of times, some number of days or weeks. And each of these little steps represents essentially a path through your sort of corporate hierarchy until you finally get value delivered, the information flows. And what we know about things like long value stream maps with lots of queues in them is that we end up with this problem of impedance mismatching in organizations. In much the same way that, when we get plaque buildup, our heart is beating against itself. When we create queues of work in our organizations, we actually have the same thing happening. We end up basically blocking the corporate arteries, blocking the way work gets done. So things like change request boards, for example, that's essentially, every time you have to go to a change request board to request maybe a change of design or something like that, essentially you're pausing everything. You're essentially like blocking the corporate arteries for a period of time before unblocking them. And that sort of puts pressure on the corporate blood supply, if you like. So as I say, when we put queues into the system in organizations, either it's queues of work, raising Jira tickets, when we have backlogs, when we have to wait on people to do stuff, that's the equivalent of blocking our corporate arteries. And all of this stuff, the depth of hierarchy and impedance mismatching causes things to slow down. It is, I'm afraid, as Agent Smith would say, an inevitability. comes on to corporate metabolism. So corporate metabolism, as companies scale, they tend to add more processes and hierarchy. And this is for various reasons, because you need to keep information flowing. People can't manage more than a certain number of people, etc. Or you might build up things like risk management theatre, which Steve Smith talks about when something went wrong once in the past. So we have to solve that problem with more process rather than think about the root cause. We'll just add another process step in, more testing, more regression testing, more integration testing, more performance testing, rather than actually try and solve the root cause. And what you end up with is these really long value streams where things take a long, long time to get done, and deep hierarchies. Things slow down because of this. But as I say, we also deliberately block our corporate arteries in organizations by imposing these stoppages, if you like. So the question is, can we identify the signs of aging, corporate aging, if you like? Can we identify the fact that our corporate metabolism is slowing and act to take action to help, if you like, or to solve that problem? A little coffee. Been talking for a while. And I think we can. And I think some of the most important work that's happened in the last, however many years, in terms of what we do as software engineers, as software architects, as quality analysts, as business analysts, as product owners, has been the work that's come out of the State of DevOps report, which is summarized in the book Accelerate, the lead author being Nicole Forsgren. This takes and summarizes, as I say, the State of DevOps reports, which is original research into what makes organizations high performing. And in Accelerate, they identify 4 simple things that you can do to monitor essentially organizational health. The first one is you can look at mean time to recovery. When a failure happens in production, when an incident occurs, how long does it take to recover from it? The next thing is cycle time. They define it as from commit through to deployment into production. You can look at longer lead times as well. We often do in our teams. The idea of idea generation through to earning value is often used by the clients that I work with. The idea of change failure rates. So how often do I deploy into production? How often does that deployment fail? And how many number of deploys do I do in unit time? And I think by looking at these, by measuring these, it's the equivalent of when we go to the GP, say, or if you do it at home these days, like our watches sometimes do, it's the equivalent of taking your pulse, taking your blood pressure, taking your temperature, all those sorts of things. They act as early indicators for whether you're slowing down or not. And then we can act to optimize them, right? Why do we exercise? Well, exercise is good for reducing our blood pressure, and so on. So I think we can identify the signs of aging. I think these 4 key metrics, the key thing is these are leading indicators of organizational health. They're not trailing. By monitoring these things, we can take action in advance of bad things happening, if you like. So they're leading indicators, like monitoring heart rate and blood pressure. But you should remember, any improvements that you can make with these, by monitoring these and trying to improve your processes, you're actually limited by hierarchy and scaling laws. You're never going to get better than that 85% implied by hierarchies if you are in a corporate hierarchy. This is the next bit of bad news, I'm afraid. It gets a bit sad, this talk, before it gets better. So companies also die. They are mortal, much like humans, much like mammals. And in fact, it's surprising that the half-life of a company on the stock exchanges is about 10.5 years. There's about 50% churn every 10.5 years on the exchanges, which is surprising. It was surprising to me when I found that out. And why is that? Why do organizations fail? Well, it seems to be there's less information out there. There's less research done on this because, of course, many organizations are much more secretive. The information is not so much in the public domain, but it seems to point to the fact that large organizations spend less of their revenue in R&D. And the analogy with biology is that as you get older, you spend less energy on cell repair, right? On repairing cellular damage that's caused by cells are being replaced in DNA, not making exactly accurate copies. And it seems to be the same thing in organizations. R&D takes the same form as essentially long-term cellular damage. So if you don't spend as much money on repairing the thing that made you successful to start with, then eventually over time, you're going to get slower and slower and slower, and you're going to eventually sort of run out of steam. And this is one of the core factors with organizations failing. Plus, bigger organizations tend to add more processes, more constraints in, more stages. We solve a process problem by adding more process rather than taking process away often. And often corporate hierarchies grow and grow and grow and grow. They get deeper and deeper and deeper. And we know that hierarchical fractal networks imply sublinear growth. So good thing is you do gain economies of scale for infrastructure as you grow, as you scale. So you only spend 85% of the amount as you double in size. But you also achieve sublinear growth in revenue. And this seems to be because of this idea of corporate metabolism slowing down and corporate mortality. As you get bigger, you get deeper hierarchies. This implies slowing of things down, that things slow down. And it also implies this idea of sublinear growth in revenue. And you decrease the organization's metabolic rate unless you take really good care to invest in the things that made you in the first place, if you like, the cells in a human, or the products and R&D that started your organization. But saying that, there is some good news, because there is a type of thing that also displays a different type of growth. And that's this idea of returns to scale. So once you do have this idea of sublinear scaling, you also have superlinear scaling, super exponential growth. So as X doubles in size, Y increases by more than double. You get more out than you should when you double. And cities get both. You get different types of growth in cities. So you get innovation, so socioeconomic factors, innovation, wages, number of professionals, but also crime and disease and pollution, they scale superlinearly. But infrastructure scales sublinearly. And interestingly, this idea of walking speed, if you go to a big city, everyone seems to be walking around faster. They did some research on this, and it is actually true. As you double the size of a city, people do walk faster. Walking speed increases by about 1.10, which is up to the limits of your legs, clearly. And the reason that they get superlinear growth is because the socioeconomic factors are driven by social networks, the networks of people and their relations with other people. And that's this idea of a small world fractal space filling network. Whilst we have a hierarchical network, I talked about previously, hierarchical fractal space filling network, you also have this idea of a small world one, the social networks that we all operate within on our devices as well these days. And it seems to be around this idea of Dunbar's number. So the concentric circles, if you like, of widening numbers of people that you know with lesser degrees of influence over you, if you like. So you've got, 5 is the Dunbar's number for your nuclear family. 15 is probably, is your sort of extended family. 50 is your very closest friends. 150 is the sort of friends and acquaintances, and 500 and so on. And just to drive this point home, this is my nuclear family. Actually, there's 6 of us, so I've got to decide whether I love my wife or one of the kids less, which is awkward. But then, this is our wedding. Certainly in the UK, weddings are about 150 people normally, if you can afford it. This is our wedding. We had about 150 there. And then, this is a conference. This is YOW, or this sort of conference, where you get bigger multiples of people who are interested in the same things as you. And this seems to be because of our evolutionary background. We grew up with small groups, essentially living in caves as hunter-gatherers, and then we banded together to form bigger units, and banded together to form bigger units in villages, and then eventually the growth of cities started, or bigger conurbations, and we've ended up with these sort of mega cities. So, just to summarize a bit, we've got this idea of returns to scale versus economy of scale, and the maths is pretty clear on this. Hierarchical networks that exist, as I said, in the different places I've described already, that implies sublinear growth. But small world networks implies superlinear growth, faster growth than you'd expect. And one of the reasons because of this, if you think about cities tend to grow by adding bits on the side. They don't often remodel the whole in a city. They add new suburbs. They grow out in a sort of crinkly, fractal way. And in fact, interestingly, you can measure the health of a city by measuring its fractal dimension, which is the crinkliness of its boundary. But this is how cities grow. So as cities grow, they get economies of scale for infrastructure, again, returns to scale for socioeconomic factors, and they don't die. Most cities stick around for a long, long time. Basically, you get 115% more stuff for 85% of the cost. And that's why cities are so successful. So here's the thing. Are there any existence proofs out there of organizations that have sort of learned the lessons around small world fractal networks, or how to achieve superlinear growth? And I think there are. I think we can point to a number of organizations that have grown in a particular way, both in terms of organizational design, but also in terms of the way their software inside those organizations is built and delivered. First to point out is that Spotify, right? So the Spotify model, which obviously is very, very famous, and I know everyone at Spotify, well, people will tell me that Spotify don't do that anymore. I actually know that. They've evolved it obviously past the point of the Spotify model, which is the whole point of it. But the Spotify model is really an attempt to create a series of interlinked but loosely coupled teams, small world network teams, if you like. ThoughtWorks, actually, we've grown in this way by adding new networks onto the side rather than expanding an existing network. You don't find any 30,000 person developer centers in ThoughtWorks. What we tend to do is we'll build another office somewhere, we'll expand into a new region, much like we've just acquired Generalized Solutions in Romania, actually. So we're super excited about that because we now have a presence in Romania, which is fantastic. But we tend to grow in that sort of way, by adding more social networks onto the side. And yes, we have a loosely coordinated global structure, but it is a really shallow hierarchy at the top. Valve Software, the computer games manufacturer and publisher, well, I mean, there was a leak of their handbook, of their employee handbook some years ago, and they actually describe their organizational structure essentially as a small world fractal network in that employee handbook. It's kind of out there in the open. And then finally, we've got Amazon. So back to where we started. This idea of Amazon, the Amazon two pizza teams and things. So if you think, back in the famous memo that was sent back in 2004, which was essentially guided the growth of Amazon to where it is now, was all around essentially imposing constraints, forcing functions in place to drive small world network growth. If you think about it more deeply, this idea of you have to communicate via interfaces, you can't sort of communicate via talking to each other's databases anymore. You have to put clear boundaries in between different social networks. You must externalize all these interfaces, and essentially that leads to them being able to monetize them later. And then, of course, famously, two pizza, or in other words, Dunbar number teams and multiples of Dunbar number teams separated cleanly. So these different small world networks separated cleanly by interfaces, both in terms of software architecture, in terms of how the Amazon software architecture is put together, but also in terms of their organizational structure. Conway's Law again. And if you think about how AWS is structured now, I think it's pretty much out in the open. Each of the product lines is created by a entirely separate team, and you can see this in the effect of this in things, or some of the suboptimal effects in things like API design. Often API design isn't very consistent across the different products that AWS offer. But what they get from that is the ability to very quickly add new teams. In fact, going back to the start, the person who sort of got me thinking about this to start with, they sort of said, the only limits to how many new products we can add, more or less, is the number of ideas we have and the number of people we can hire. So some of this should go to explain why the numbers are as they are for AWS. A super exponential growth in revenue compared with employee count, bucking what would normally be the trend in the markets for sublinear growth here, sub-exponential growth. And the interesting thing is, in the AWS reInvent conference that happened at the end of last year, isn't it? November last year, the new CEO of Amazon, he actually presented a graph showing very, very similar numbers to this, which made me very happy because I haven't got it completely wrong. So again, this exponential 1.15, faster than exponential growth. So as most companies get bigger, it gets harder to get bigger. It gets harder to add new people, it gets harder to build new products. But as Amazon gets bigger and some other companies get bigger, it gets easier to get bigger based on the ability to quickly add decoupled cohesive unit off to the side as essentially a small world network, and grow the organization via small world network growth. So that's kind of what I have for you today. I'm going to summarize a little bit what I sort of talked about. So back to Geoffrey West and the book Scale. Quantities that do not change when other parameters of the system change, they play a special role in science. And back to what we said at the start, we can attempt to describe what we see as common characteristics for architectures that fit the label of microservices. And a lot of this is about decentralization. It's about decoupling. It's about cohesion. It's about growth at the edges, pushing decision-making out and down, and avoiding hierarchies. And as I say at the start, are we looking at something that's sort of an underlying set of principles around small world networks? So social network effects, they imply super exponential growth. In contrast, sublinear growth implies mortality. So the consequence of this, I think, and the consequence of me finding out about this is, when we're in organizations, we should be looking to experiment with different types of organizational structure that aren't hierarchy. In fact, I'd probably go further and say we need to limit the depth of our hierarchy as much as we possibly can and encourage growth in a small world social network way. And we should question those hierarchies. Why do they exist, and can we remove them? So this is the original research that this talk is based on. I can't say I did it myself. It's a summary of some amazing work that's been happening at the SFI and also elsewhere with Nicole Fulter and Jez and Jean's work with Accelerate. Also, of course, with reference to Donald Reinertson, who wrote the brilliant book, Principles of Product Development Flow. So here's the original search, which is summarized. So Louis Betancourt, some amazing stuff around scaling in cities, and then the original West Brown and Enquist paper around scaling laws in biology. So there you go. That's me, and I guess I'll just say thank you and leave it at that. And now I'll stop my share.
Thank you, James. Do you also have the time to answer a couple of questions?
Yes. I'm not on mute. Good. Okay, I thought I'd myself and then switched. Yes, I do. Yes, please.
So basically, what do you think about the communication culture? How important do you feel that is in the context of building such applications?
Communication culture. Can you expand on that, maybe? How do you mean?
The actual question is, communication culture is everything, isn't it? So I put words in.
Sure. Yeah. No, fine.
Absolutely.
I think so. No, it's trying to create those. It's trying to create the shortest possible number of hops between people who need to be able to make decisions together, right? So, good example I mentioned at this workshop was we had an open space where with Mel Conway and a few others, and we were talking about the uses I said we put Conway's Law to over the years. And one example of that was, Adrian Cockcroft talking about his time at Netflix, which is of course a microservices, famously microservices fine-grained SOA architecture. And what they did is they made sure they sat the teams who needed to talk to one another next to one another. So, for example, the UX, the UI teams would be sitting close to the platform API teams, because that's the people they need to talk to in order to get change done, essentially changes made, really. And then the platform teams are sitting next to the sort of first set of actual more aggregate services sort of teams. And as you go down the stack, there's the teams are sitting further and further away. So I don't need to talk to people maintaining our Cassandra instances all the time. So, or, designing whatever it is, they're designing network design. So they're sitting a bit further away, but I do need to talk to these people so we can talk about, do conversational change and things. So absolutely, it's everything, I think. The key thing is, we did some research in ThoughtWorks some years ago now, actually. I've used it in other talks. It was in Australia, a very big telco, over 18 months, and we tracked the impact on cycle time of stories, user stories leaving your team. And the impact was an order of magnitude. So anytime you had to go outside your team to get something done, you're going to blow your cycle times by 10 times, or actually more. It was more like 12 times. So the closest you can keep people that you need to talk to and you need to get help with, the better. Of course, you can invert that model, and this is why platforms are so important now. Is if you can offer self-service, that short circuits that 10 times cycle time problem, right? Because I don't have to raise a ticket to get an EC2 instance. I do it myself, and that inverts that. So yeah, there are some caveats, but yes.
I have to say, I love your example with Netflix, because I think one of the things that stuck with me from yesterday's architecture event is that you know, a microservices architecture starts to be based on the actual organizational architecture.
Yeah.
In the company. So I love how they turned this around and designed the organization based on the architecture.
And yeah, it's a combination of the two, right? You know, because they'll converge is the idea essentially. So yeah, design the organization you want, and the architecture will follow, kicking and screaming. Is my colleague Evan Botch's quote on that. Yeah.
Yeah, very very good point.
Yeah, and also to chip in on that, I think for me it's something that this I know pandemic brought to the attention, because for instance you had a lot in projects with multiple teams, you had a lot of informal communications between members of different teams.
Yeah.
But now you need to schedule a call for everything, and in such projects with 10, 15 or even more teams, you see that if you see a lot of communications and meetings between teams, then you see how, I know, tightly coupled your software design is.
Yeah, no, yeah, that's a really interesting observation. I haven't thought about it in terms of actually you could use it as signals, but you could, couldn't you? You could actually detect signals, which is how many times I'm having to speak with that other team, right. And use that as an indicator. Yeah.
Yeah, and before this, this were, I don't know, maybe small chats around the morning coffee or at noon, but now they're more obvious. Now you realize them better.
Yeah. I mean, there are some really interesting implications, I think, with the pandemic and this research. You know, it's, well, that everyone knows what exponential and super exponential growth looks like, because over here it's, you know, everyone's obsessed about the R number, right? If the R number is bigger than 1, that's super exponential growth. It's like bad. Yeah, but also in terms of, you know, in terms of people living close together in cities, you know, if people are going to be able to move away and work more remotely, what does that mean for serendipitous conversations? What does that mean for learning? What does it mean for culture of organizations? What does it mean for growth? You know, how do you grow less experienced developers who part of the growth is sitting with more experienced people, not necessarily working with them, but hearing the conversations they're having or seeing the diagrams they're drawing? Part of that is growth, isn't it? You know, so I think there's some really interesting implications. Yeah,
definitely.
I have to ask, do you feel like this new paradigm of working from home will affect this hierarchies in organization and the corresponding serendipity, let's put it like that?
I'm not very good at predicting the future. What I will say is, if you look at the research that MIT did with Microsoft into sort of basically, Mel Conway published his paper, his original research, right? And then it was sort of, we don't really think that's right or whatever. People disagreed with it. And then MIT and Microsoft did some further research, which then backed up his original results. But in that research, the most decoupled, essentially, the quote better, but the most decoupled software was delivered by open source team, actually. So it's interesting when you think about how when we're all now in a place where we're all more like open source developers, sitting on our own, you know, writing code and pushing it, as opposed to sitting in teams. You know, we've sort of forced into that model. So I do wonder whether that's going to have an influence or not. Or certainly that I would predict there would be. But yeah.
Yeah, the next couple of years will be interesting. Certainly. I think we've covered. There is one more for Jahan. In terms of analogy, can we think of a counterpart for accelerate measures in a living organism?
Yes, I think that's what I was sort of saying. You know, I think the change failure rates and all that sort of stuff are the equivalent. I'm not saying they're the exact analog, but they're the equivalent of the similar signals that we would use for ourselves or for other mammals. The interesting thing is, of course, with mammals, we are born, we then grow and reach a certain size and we stop. And then there's a fixed set of measures that we can use at different ages to say whether you're healthy for your age. So what's your blood pressure? What's your average heart rate? And then you can work to improve it, right? But as I said, exercise, reducing your salt intake, whatever it is, and they act to do things to your metabolism. The thing is with companies, they don't stop, right? So they're born, they grow, they keep growing, 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 and we know that as you keep growing, metabolism slows down in animals because of the scaling laws. The same thing happens with companies. So I think the 4 key metrics are the equivalent of the blood pressure and things. But I think the interesting thing is, at what point in the life cycle, you could argue, of a company and the organizational, the structure, the teams, and how fast they're going and things, the change failure, those 4 key metrics it implies they should be better when you're smaller, essentially, than when you're bigger. But can you reverse it? How much can you reverse it by acting on them? I think as you get massive, it's a bit depressing, because in some very big organizations, there's not a lot you can do, actually. it's a bit tricky to do stuff to make change.
Yeah, especially after a certain level of growth.
Yeah.
Because I think, while we're talking, there was another question that popped up, that is transformation possible if a company is deeply hierarchical? Probably it is, but it gets more difficult. The more difficult, the more bigger the size.
I think so, and that's like then there's a lot of stuff around politics there at that point, isn't there? Because people tend to, you tend to accrue people, and that's like a sign of how important you are and how big your budget is and all that kind of thing. It's very difficult to get around that. What we are seeing more of is the sort of there's a name for it, I can't remember, disrupt yourself model. That's it, I think, or something along those lines, where rather than actually force change in the original organization, you actually start up a challenger and just try and disrupt your own business. So you start again off to the side, kind of thing. We see this a little bit with insurtech. We've seen this a little bit with fintech, where you rather than fix the problems in the 200-year-old company, you start up a new thing on the side, starting from scratch, essentially. But that doesn't address the original problems. I think yes, you can. And the other thing I think I'll point out is, in most big organizations, there are tremendous gains to be made by looking for things like failure demand and trying to reduce failure demand and improve throughput. I think that's the real key thing. You won't get to be maybe as fast as you'd like, but by putting in the things we talked about at the start, actually, things like continuous delivery, CI, making sure you've got fast, efficient change processes into production, removing things that you don't necessarily need from your value streams. You can make massive gains, I think, in terms of throughput. In fact, I would challenge everyone to draw a value stream map of your current software development process, right, from where ideas come from, and identify all the different points that you're generating either failure demand, so things are coming back up the pipe like defects, or you're having to wait on things to happen. So there's queues or meetings or whatever. I bet you, just by drawing it out and putting the numbers in, you'll immediately be able to improve your throughput by 100%, because you'll be able to we don't need that, don't need that, don't need that, don't need that.
Yeah, that's a cool exercise.
Yeah, it helps
now
you
we
get
have some
things
homework.
out of your head.
Yeah, that's your homework. There you go.
All right. Well, thank you very much, James. Again, lovely to talk to you, and it's been a pleasure. Hope to see you again at Codecamp.